Hello there, this is Professor Haywood, and this is lecture 2.1. And um, I'm recording this lecture from home, which is a little bit different from my normal setup. I apologize if you hear my dog snoring in the background. Uh, I'm excited to start this unit. I enjoy probability a lot. I enjoy the whole course, of course, but probability is a lot of fun. The reason that we're talking about probability is because we've done a lot of exploratory analysis in Unit 1, and what we would like to do is take what we are seeing about the samples that we have collected and extrapolate to the entire population, right? So we might notice that, oh, the sample mean is this. What can we say about the population mean? In order to make that extrapolation, that's what we're going to be doing in Unit 3, okay? But in order to make that extrapolation, we have to understand a little bit about probability, right? All of the inferential statistics that we're going to be doing in Unit 3 are built on probability models that we need to take some time to understand, and that's the topic of discussion now in Unit 2. We're going to start at the very beginning with probability, so we're going to start with the basic notion of probability, which is the idea that the probability of an event occurring is the number of ways that that event can occur divided by the total number of possibilities, right? Because we're going to be counting the number of ways something can occur, we need to talk a little bit about some counting techniques. And so that's where we're going to start in 2.1. This section is about counting techniques. And when I say counting techniques, I don't mean counting by fives or something like that. I mean, we're going to talk about things like combinations and permutations. So let's get into it. What you should have is you should have the notes downloaded or printed or something so that you're ready to kind of follow along. And then we won't be working with Excel in this unit very much, if at all. But I will show you how to do some things in this section on Desmos, on the Desmos calculator. So you might want to have the Desmos calculator opened up so that you're able to follow along with those examples. And so that's that. Without further ado, let's get into section 2.1. Okay, so here we are in 2.1. This section is all about counting techniques. And we'll just start off with a really kind of a simple example just to kind of get us thinking about how we might need to count up the different ways that something can occur. So this example says, the fixed price dinner at a restaurant provides the following choices. For an appetizer, we can choose super salad. For the entree, we have the choice of baked chicken, broiled beef patty, baby beef liver, or roast beef, none of which sounds particularly appetizing to me. And then for dessert, we can have ice cream or cheesecake. And then the question is, how many different meals can be ordered? Okay, so let's think through this a little bit, right? For your appetizer, you can have super salad. Let's say that we go with soup, okay? So then for our entree, we have 4 choices, right? We can choose the baked chicken, the broiled beef patty, etc. So if we choose soup, then we have 4 choices for entree. If we choose salad, then we also have 4 choices for entree. So I think by the time we've chosen our appetizer and our entree, we're going to have 8 different meal options, right? Soup and baked chicken, soup and broiled beef patty, soup and baby beef liver, right? Soup and roast beef, and then we have the same options for salad. Salad and baked chicken, salad, broiled beef patty, right? So that's 8 possibilities in total. So 8 possibilities, but we still haven't chosen a dessert. There are 2 choices for dessert. So starting with any of our 8 choices for appetizer entree combinations, then we could also add ice cream onto each of those or cheesecake onto each of those. So in total, I think we're going to have 16, right? 16 different meal possibilities. Some of you are pretty intuitive mathematically, and you might say, oh, well, yeah, that's obvious because we had 2 choices for appetizer and 4 choices for entree and 2 choices for dessert. So it's just intuitive that this is going to be 2 times 4 times 2, which does indeed equal 16. And that's absolutely correct. Your intuition is serving you well if that's what you were thinking. This is called the multiplication property of counting. And we can use it to count all sorts of things. And we'll talk about some slightly more complicated examples in a second. But this is called a tree diagram. And so here's a tree diagram that sort of verifies that our reasoning is correct, because it lists out all of the possible, right, all of these possible meal options. Okay, so moving on. So we'll talk about different kinds of counting. We'll talk about counting with repetition, and then we'll talk about permutations and combinations. Okay, so let's look at another example. This first one says, the International Airline Transportation Association assigns 3-letter codes to represent airport locations. For example, the code for Fort Lauderdale International Airport is FLL. How many different airport codes are possible? So using the multiplication property of counting that we talked about on the previous page, we could say, well, the total number of airport codes are going to be the number of ways to choose the first letter in the code times the number of ways to choose the second letter, right, times the number of ways to choose the third letter. Okay, for the first letter, well, there are 26 letters in the alphabet, right? So we would have 26 options for that first letter. Now, it looks like repetition is allowed here, right? We're allowed to repeat letters. And so if there are 26 options for the first letter, there are still going to be 26 options for the second letter. And then there's also going to be, of course, 26 options for the third letter. So in total, right, this is going to be 26 times 26 times 26, which we could punch into our Desmos calculator, right? 26 times 26 times 26 is 17,576. $17,576. Okay, now you may notice that 26 times 26 times 26 is just 26 cubed, right? Because you had 26 options for each letter, and you needed to choose 3 letters, so it would be 26 to the third power, and that's true in general. Okay, so when repetition is allowed, for counting with repetition, right, we have a shortcut, right? It's exponents. We can just use exponents. So let me give you another example of this. Number 2 here says, license plate numbers in a certain state consist of 6 symbols. The first 4 symbols are letters, and the last 2 symbols are digits, 0 through 9. How many different license plate numbers are possible? Well, we have to choose, first we have to choose 4 letters, okay, and then we need to choose two digits. So for the letters, there are 26 letters in the alphabet, and we need to choose 4 of them. So we're going to do 26 to the 4th power. For the digits, now you might say that there are 9 digits, but you have to count the 0, right? So 0 through 9 it's 10 digits, right? There are 10 digits, 0 through 9. So we have 10 digits to choose from, and we need to choose 2 of them to go on our license plate. So it would be 26 to the 4th power times 10 to the 2nd power. And again, we can go over to our calculator. We said 26 to the 4th power times 10 to the 2nd power, 10 squared. So that comes out to, wow, 45,697,600. Let's see if I can remember that big number. 45,697,600. Whoops. 45,600,000. Ooh, I already forgot it. 697,600. Okay. So that's how counting with repetition works. We'll use exponents. We have a nice shortcut for that. How However, repetition is not always allowed. So let's give a couple examples of that, right? Number 3 here says, 3 members from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. The first person selected is the chair, the second person selected is the vice chair, and the third is the secretary. How many different committee structures are possible? Okay, well, there are 14 members on the committee, and basically we're asked to choose the leadership of this committee, right? The chair, vice chair, and secretary. So we have 14 members to choose from to fill the chair position, right? We need to choose 3 people, chair, vice chair, secretary. And we're going to multiply these, right? Multiplication rule. 14 people to choose from to serve the chair position. But notice that once we've filled that position, there are not 14 people left to choose from. There are only 13 people left to choose from, because it doesn't make sense to choose the same person to serve as both the chair and the vice chair, right? So we would have 14 choices for the chair, 13 for the vice chair, and then 12 for the secretary. Now, this might distress you a little bit, because you might think, well, but how do we know that we need to choose the chair first? What if we choose the vice chair first? But multiplication is commutative, right? You could think of this as you've chosen the vice chair, and then the chair, and then the secretary, and it's exactly the same thing, right? It comes out to exactly the same thing. So anyway, total number of committee structures is going to be 14 times 13 times 12. So let's see how much 14 times 13 times 12 is. That's 2,184. Okay, here's another example. It says you've just been hired as a salesperson for a company that produces educational software. On your first day, you must travel to 7 schools to introduce yourself. How many different routes are possible? Or routes? I don't know. Or whatever you get, however you guys pronounce it, routes or routes, I don't know. I use those pronunciations interchangeably, but okay. So 7 schools, you have to travel to 7 schools. How many different routes are possible? Well, I'm going to have 7 choices for the first school, but then I'm not going to visit that school again, right? I'm going to go to the next school, and so there are only going to be 6 choices left for the next one, and then 5 after that, and 4, and this is going to keep going until I get to the very last school, right? Now I've chosen all 7 schools, 1, 2, 3, 4, 5, 6, 7. So I've got all 7 schools there accounted for. So we can go ahead and do this multiplication, 7 times 6 times 5 times 4, etc. So all the way down to 1. That's 5,040. Okay. These types of problems are called permutations, right? Let's give a definition of that. So a permutation is an arrangement in which R objects are chosen from N distinct objects without repetition and where order is important. Okay, so those 2 things, we'll underline those, right? So repetition is not allowed, the order matters. Okay, so ABC would be considered different from BCA. We use the symbol NPR. We read this N permute R, right? So this is N permute R. It represents the number of permutations of R objects selected from N objects. To compute a permutation in Desmos, you can either find the permutation button under the function menu, or you can just type in NPR, and then you're going to put in the number of objects you have to choose from, and then the number of objects that you want to select, okay? So for example, example 3, this was, we wanted to choose 3 members from a 14-member committee where the order matters because the first person chosen is chair, right? So order matters, and repetition is not allowed. We can't choose the same person to serve as both chair and vice chair. So in terms of permutations, we would say, well, we have 14 committee members and we want to choose 3 of them. So we would call this 14 permute 3. In the case of example 4, we would say, well, we had 7 schools that we wanted to travel to, and we needed to travel to all 7 of them. So we would call that 7 permute 7. And we can do both of these in Desmos. So 14 permute 3, I'm going to find it under the function menu. So if I click on the function menu, then there's this permutation button down at the bottom left. And I can just type in now 14, comma 3 to do 14 permute 3. If I want to do 7 permute 7, I would do the same thing, right? Hit the function menu, permutation, and then I want to do 7 permute 7. And so those are, you can verify, right? Those are the same answers that we got when we did it the long way. So looking at number 5, we're asked, in how many ways can horses in a 10-horse race finish first, second, and third? So we've got 10 horses. The questions we should ask ourselves to know whether or not this is really a permutation problem is repetition allowed, and does the order matter? I would say repetition clearly is not allowed. It doesn't make sense for the same horse to finish in both first and second place, right? So repetition is not allowed. Okay, so this is a counting problem without repetition. And the order definitely matters, right? If Seabiscuit gets first place and Secretariat gets second place, that's a different outcome from Secretariat getting first place and Seabiscuit getting second place. And yes, those are the only horse names that I know. They're just from movies. But yeah, so the order matters. So this is definitely a permutation problem. I know right off the bat that this is a permutation problem. I have 10 horses that I need to choose from, and I want to pick the top 3 winners. So this is going to be 10 permute 3. Now let me just comment real quick. When you are doing your work on these kinds of problems, on like a problem set or a test, I definitely want to see you write this symbol, okay? I want to see you show your work. So make sure that you're writing out that work. And this is for your own benefit, because if you get the wrong answer and you didn't show me any work, you just wrote down like your answer, then I can't give you any partial credit for that, right? But if you show me your work, then I can see, oh, okay, so like this student, I could award some partial credit based on how much is wrong and how much is right. Anyway, so write down your work. We'll say this is 10 permute 3, and then we'll go over to Desmos to get our answer. So 10 permute 3, 720. Okay. So that's permutations. The last counting technique that I want to talk about in this section is combinations. Combinations are used when the order is not important, okay? So when repetition is not allowed, just like with permutations, but unlike permutations, the order doesn't matter here. So ABC would not be considered different from BCA. So an example of this would be like pizza combinations, right? A pepperoni and olive pizza is the same as an olive and pepperoni pizza. Okay, so if you're counting the number of possible pizza combinations given a set of toppings, the order would not matter. We wouldn't count a pepperoni and olive as different from an olive and pepperoni. Okay? And we'll use this symbol to represent combinations. We read this N choose R. Okay? And again, you can find this function under the func menu in Desmos, or you can just type in NCR. Okay? So an example of this says, number 6 here, Roger, Ken, Tom, and Jay are going to play golf. They will randomly select teams of 2 players each. How many possible teams are there? And then we're asked to verify our answer by writing out the possible teams, I think because there are probably not very many. But let's see. So with names like Roger, Ken, Tom, and Jay, what else would these guys be doing? They're going to play golf for sure. Okay. We want to select teams of 2 players. Well, we have 4 individuals here to choose from. We need to select 2 of them to be on a team. And repetition is not allowed here. It doesn't make sense for Roger to be on a team by himself, right? But the order doesn't really matter. If we choose Roger first and then Ken, that's the same team as choosing Ken first and then Roger, okay? So the order doesn't matter. That makes this a combination problem. So this is a combination problem. We have 4 people to choose from, and we need to choose 2 of them to be on a team. So in Desmos, we would go to the function menu, choose NCR, and we want to do 4, choose 2. So that comes out to 6. And there's our answer. We were asked to verify our answer by writing out the possible teams. So, okay, one possible team would be like Roger and Ken. Another possibility would be Roger and Tom. And another one would be Roger and Jay. And those are all of the possible teams that include Roger. But then there are other teams, right? Like Ken and Tom, or Ken and Jay. And then we could also have Tom and Jay. And I think those are all of the possibilities, right? That's all 6 possible teams. Another example. How many different simple random samples of size 4 can be obtained from a population whose size is 20? This is a good question for a stats course, right? How many different simple random samples could we obtain, right, from a population of size 20 if we want a sample size of 4? Well, in a simple random sample, repetition is not allowed, okay? And the order doesn't really matter if you're collecting a random sample. The individuals that you end up choosing to be in your sample, they don't have any particular ranking. So you're going to get the same sample, regardless of the order in which the individuals were chosen. So order doesn't matter, and that makes this a combination problem, another combination problem. We have 20 individuals in the population, and we need to choose 4 of them to be in our sample. So 20 choose 4. Let's see what that is. Uh, 20 choose 4. 4,845. Okay, so lots of different potential simple random samples. So that'll do it for us. As a summary, what I would say is that there are, of course, other types of counting problems that we could introduce here, but the ones that we've covered, the 3 that we've covered, will be enough for our course. If you're interested in these kinds of counting problems, then you should take a course in combinatorics, right? It's a really interesting topic, and there are people who there are mathematicians who specialize in combinatorics. It's like they like that's what they do research in. So anyway, it's a deep topic, and we've just spent, I don't know, a half an hour talking about it, right? So we've just really barely scratched the surface here, but it's enough. This will give us enough to work with to do what we need to do with probability in this course. So here's a summary of these techniques that we've talked about, right? We've got it in a table form here, and then a little flow chart down here. And I think the flow chart really sums it up pretty nicely. As far as this class is concerned, it's not going to get any more complicated than this for counting techniques. So when you encounter a counting problem, the first thing you should ask yourself is repetition allowed? And if the answer is yes, then we'll use exponents. If the answer is no, then we have to ask ourselves a second question, right? Does the order matter? And if the answer is yes, we'll use a permutation. If the answer is no, then we'll use a combination. And that's how we'll make our decisions. So let me just run you through 3 more examples to kind of illustrate how I would think about these kinds of problems if I were going through this myself. These 3 problems are intentionally very similar to one another, okay? Because I want them to be as close to the same as possible so that you can see where they differ, right? And anyway, so let's get into it. One year at the Wasco Rose Festival, I grew up in Wasco, California, by the way. I don't think they have a Rose Festival anymore, which is kind of sad, but okay. So it says 1 year at the Wasco Rose Festival at the Wasco Rose Festival Floral Arrangement Contest, there were 172 entries. 5 judges went out to select their favorite arrangement to award a grand prize. Each judge got to choose one arrangement, but no arrangement was supposed to receive more than one prize. All of the prizes were the same. And how many ways could the 5 prizes be given out? So if you're at all like me, you read through that and your head is just kind of spinning a little bit, like you don't know what you just read. So what you should do is take a moment, maybe pause the video, read the question again, make sure that you're absorbing the information in the question before you try to write down any answers, okay? But let's see, there were 172 entries, and some judges went out to award a grand prize. Each judge, we had 5 judges, and they each got to choose an arrangement to give a prize to. All of the prizes were the same. Okay. So since no arrangement, so let's go through our process, right? The first question we ask ourselves is repetition allowed? And I would say, since no arrangement is supposed to receive more than one prize, we can't have a repetition, right? We can't have 2 judges awarding the same arrangement with their grand prize, right? So no, repetition is not allowed. So we won't be using exponents here. We do have to ask ourselves a second question then, right? Does the order matter? But here I would say, all of the prizes are the same. It's not like the first judge awards first place and the second judge awards second place or something like that. All of the prizes are the same. So I would say no, the order doesn't seem to matter here, and we would use a combination. So this is a combination problem. There are 172 entries, and the judges need to choose 5 of them. Okay, so it would be 172 choose 5. This is going to be a very large number, I think. Well, let's see. 172, whoops. 172, choose 5. Oh yeah, that's such a large number that Desmos doesn't have enough digits to store it. This 1.18, etc., times 10 to the 9th means we need to move this decimal 9 times to the right. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. Oh, goodness. So I'll do my best. This is 1.18300. 1.18300. What other digits did we have here? 946. 946 times 10 to the 9th. Okay, if we wanted to write that out, so this is scientific notation. If we wanted to write it out in standard form, we would move the decimal 9 times to the right. Okay, so 9 times 1, 2, 3, 4, 5, 6, 7, 8, and 9 means we would have to add another 0 to the end of this. Okay, so we would have, let's see, 460 and 009 and 183, and then a 1. Okay, so this is 1,183,009,460. So a very large number. Okay. Number 9 says, a different year, at the Wasco Rose Festival Floral Arrangement Contest, there were also 172 entries. 5 judges went out to select their favorite arrangement to award a grand prize. Each judge got to choose one arrangement, but this time there was no restriction on the number of prizes an arrangement could receive. All of the prizes were the same. In how many ways could the 5 prizes be given out? So once again, you might need to pause that and reflect a little bit. But okay, no restriction on the number of prizes an arrangement could receive. So this time I think repetition is allowed, right? Repetition is allowed. We'll use exponents. So we have 172 entries. There are 5 prizes. Oh wow, this is going to be a huge number, right? We have 172 entries. Okay, so there are 172 choices for the first prize to be given out, but then we need to award 4 more prizes, so that's going to be 172 times 172 times 172, 5 times, right? It's going to be 172 to the 5th power. So 172 to the 172 to the 5th power is another huge number. Okay, let's write it down. So it's 1.5053646 times 10 to the 11th. Okay, so we're going to have to move that decimal 11 times to the right if we want to write this in standard notation. 1, 2, 3, 4, 5, 6, 7, 8, and then we'll have to add 3 zeros to the end, right? 9, 10, 11. Okay, so let's see. 1, 2, 3, 1, 2, 3. So this is going to be 150, 536, 646, 000. So that's 150,536,646,000. Okay, one more. Number 10 here says, another year, at the Wasco Rose Festival Floral Arrangement Contest, there were once again 172 entries. What a coincidence. This time, a panel of judges viewed each arrangement and then collectively chose first place, second place, third place, 4th place, and 5th place. In how many ways could the 5 prizes be given out? So again, we ask our 2 questions, right? Is repetition allowed? And here I would say no, because it doesn't make sense for the same person to win both first place and second place, right? And then the next question is, does the order matter? And here I would say yes, right? If Bob gets first place and Sally gets second place, that's a different scenario than Sally getting first and Bob getting second. So the order matters here. That makes this one a permutation problem. We have 172 entries, and we need to choose 5 of them for our top 5 finishers. So in Desmos, we're gonna do 172 permute 5. So that's another big number. Not quite as big as the previous one, but let's go ahead and write that one down. So this one is 1.41961136 times 10 to the 11th power. So to write it in standard form, we move the decimal 11 times. 1, 2, 3, 4, 5, 6, 7, 8. And then we'll need 3 more zeros, 9, 10, 11. So I think this one is going to come out to 141,961,000. 130, or no, 141,961,136,000. Wow. Okay. So lots of ways to award those prizes. So that's how that works. That brings us to the end of section 2.1.